So today we are going to talk about the limit comparison test, and we'll see if we get past that, but we're going to at least start with the limit comparison test. So if you remember doing the ratio test yesterday, there was one instance in which the ratio test was inconclusive. And what was that instance? If that ratio between the n plus first term and the nth term was equal to exactly, if it was equal to 1. Thank you, Nick. So in those cases where that ratio test, which is generally the first test, like the first major test you're going to look at, that ends up being 1, chances are you're going to want to move on to the limit comparison test. And the limit comparison test is going to be a little bit similar to our direct comparison test, except that for this one, the convenient thing is that we don't necessarily have to have one of our series that we're looking at always be larger than or always be smaller than the series that we are actually looking at, than the one that we're interested in. What we do still have to have is we have to have 2 series that are always positive, and we have to know whether the one we're comparing the limits of, like not the one we're investigating, but the other one that we're using, we need to know whether that one converges or diverges. That should be pretty straightforward. We should normally be able to tell that fairly easily. So the way the limit comparison test works is take the ratio of the nth term of your series divided by the nth term of the series you're going to compare it to, and look for the limit as n approaches infinity. So if that comes out to be a non-zero finite number, so anything between 0 and infinity, that will tell you that either both of your series converge or both of them diverge. So that way, if you know that the one you're comparing to converges, then you know yours converges, or if the one you're comparing to diverges, then yours also diverges. Basically, what that limit is telling you then is that the nth terms of those are basically increasing at the same rate. Now, if we look at the limit as n approaches infinity of a sub n over b sub n equals 0, okay, then that should tell us that if the one we're comparing to converges, then ours will also converge, because that's indicating that the term in the denominator is larger than the term in the numerator. And so if the one that's in the denominator is going towards something larger than the one going toward the one the numerator is, and the one in the denominator converges, ours must also be converging. And likewise, if we take that ratio and get infinity, and we know that the one in the denominator diverges, then the one in the numerator also needs to diverge, just by the same sort of logic as number 2, just sort of in reverse. Does that all sort of make sense? Okay, so obviously you can probably see that there might be some issues with this test, and there are some issues with this test, which are what happens if you end up getting 0, but your series that you were comparing to diverges, or what happens if you get infinity and the series you were comparing to converges. Well, then this test doesn't work either. But this should sort of, you've got a few that filter through that don't work with the ratio test. This should filter through even more, and you'd have even less of them that you'll have to continue using a different test with. So let's take a look at this series here: 3/4 plus 5/9 plus 7/16, and so on. The sum from n equals 1 to infinity of 2n plus 1 over n plus 1 squared. And we're going to try to determine if this converges or diverges. So first off, as we look at this, does this have all positive terms?
Yes.
Yes. make a note that this, you don't always have to do this, but I just want to make a note here that this has all positive terms. Okay? And if we look, and when we're doing this limit comparison test, what we generally want to look at is the base nature of this function. So this is an n to the first, and it's an n to the second in the denominator. And so our first function, or first series that we might want to try to compare it to, will always be the reduced down version of just the base series from this, which is n over n squared. So that would be the sum from n equals 1 to infinity of just 1 over n, because the 2 instead of becoming insignificant, it's 2n over n squared, which is just like 1 over n effectively. So that's what we're going to compare it to. And what do we know about that series? We should very easily know something about that series. What do we know about that one? This is the part where you answer and say something. What do you know about the series 1 over n, the harmonic series? Does it converge or does it diverge? And thank you, Shayla. This diverges. And why does it diverge? We should indicate a reason, because of the P series test, right? We already went and proved that for n equals 1, this series will diverge. Okay? And so what we'll do is we'll just write out our limit then as n approaches infinity of the ratio of the nth term of our series, 2n plus 1 over n plus 1 squared, all divided by the nth term of the series we're comparing it to, 1 over n, and just evaluate this limit, which should be fairly easy to do. Right, this gives us the limit as n approaches infinity of 2n squared plus n. If we flip that 1 over n and multiply, and then n squared plus 2n plus 1. And what is that limit? This is the part where you tell me what that limit is. Now here we go. It's 2, right? That should be easy. That limit is 2. And since this limit had a finite value that was greater than 0, that it wasn't 0 and it wasn't infinity, it tells us that both our series and the series we're comparing it to either converge or diverge. And since the series we're comparing it to diverges, that tells us that our series diverges. So. And we'll say it diverges by the limit comparison test. Easy enough. Pretty straightforward test when it works out nicely. Good or not good? Hopefully good. All right. What about this one? 1 plus a third plus a seventh and so on. 1 over 2 to the n minus 1 from n equals 1 to infinity. What do you think we should compare this one to? Well, first off, does this have all positive terms forever? Yep, should be all positive terms, right? And as I go towards infinity, what piece of this thing becomes very insignificant? That minus 1, right? And so we'll kind of think about comparing it to the sum from n equals 1 to infinity of 1 over 2 to the n, right? Which also has all positive terms, right? So those seems like that's kind of like the base of this function as we go towards infinity. It just becomes 1 over 2 to the n. And so we'll compare those two using the limit comparison test, taking the limit as n approaches infinity of 1 over 2 to the n minus 1 over 1 over 2 to the n. And that should give us a limit as n approaches infinity of 2 to the n over 2 to the n minus 1. And what's that limit equal? As we go towards infinity, that minus 1 becomes insignificant, and 2 to the n over 2 to the n just becomes, should just become 1. Good. And so since this is a finite value between 0 and infinity, that means that either both of these series converge or both of these series diverge. And what do we know about the series from n equals 1 to infinity of 1 over 2 to the n? Does that converge or does that diverge? This is the part, there we go, yeah. Except you had to say it without the question mark, Nick. This converges. Why does this converge? No, not the p-series test. P-series, remember, is n to a power. This is a number to the n. So you got to give me a different reason why this converges. What does this series look like? It looks like a half plus a fourth plus an eighth plus a 16th and so on, right? What sort of series is that? It's geometric with r equal to 1/2, right? So it must converge. So by the limit comparison test, we can say that the sum from n equals 1 to infinity of 1 over 2 to the n minus 1 also converges. Good or no? I hope that you all saw that that was a geometric series. You didn't just not see that, right? That's a geometric series. That's 1/2 to the n power. Everybody good or no? Any questions? All right, let's do another one. You guys want to try and do this one on your own? Sure, great. No response. So we'll go with yes, you can do this one on your own. I will give you 3 minutes to try to do this one on your own. Ready, go. All right, first off, does this have all positive terms from n equals 2 to infinity? Definitely, right? And so we're going to compare this to the sum from n equals 2 to infinity. What did you compare it to? What is the base nature of this function? If you ignore all the constants and all the lower powers of n. One over n squared, exactly. So we're going to compare to 1 over n squared. And what do we know about 1 over n squared? Does it converge or does it diverge? That's right, it converges. Oh wait, nobody said anything. Why does it converge? Converges by the p-series test. Okay, so our limit then should look like the limit as n approaches infinity of 3n plus 2 over n cubed minus 2n times n squared over 1, right? If we're dividing by 1 over n squared. And what does that limit come out to be? Should be just the leading coefficients makes it 3. And so we will say by the limit comparison test, our series converges. Easy enough. All right, last one. Let's see if we can determine whether the sine of 1 plus the sine of a half plus the sine of a third forever, right? The sum from n equals 1 to infinity of the sine of 1 over n converges or diverges. So first off, yeah, I can go back for a second. First off, I'll go back for a second. Good now, Molly, or no? Okay. All right. So first question we have to ask ourselves about the series from n equals 1 to infinity of sine of 1 over n is, does this always have positive terms? Sine is positive anywhere between 0 and pi, right? So 1 is between 0 and pi, and a half is between 0 and pi, and a third is between 0 and pi. And as I go from n equals 1 to infinity, all of those values are going to be between 0 and pi. So the sine of all those things will always be between we'll always get out some number between 0 and 1, which will always be positive terms, right? These are always going to be first quadrant angles. So definitely always positive. So then the question becomes, what do we want to compare this to? Because this one doesn't quite look like all the other nice little rational functions that we had. Any thoughts on what we might want to compare this to? Okay, so if we try to do sine of n, let's just real quickly look at that. So that's a good suggestion, Darius. Sine of n, we're going to be looking at a limit as n approaches infinity of this, which would be fine. What do we end up with here? Sine of 1 over n, right, is 0, but the sine of n as n goes towards infinity oscillates, and this doesn't exist. And that creates a little bit of a problem. For one, because our limit comparison test up here said if it equals infinity, if it equals 0, or something between 0 and infinity, it doesn't exist as none of those three things. So that's an issue to begin with. In addition to that, do we know anything about the series of sine of n? Do we know if that series converges or diverges? I don't think we've talked about that and tried to figure that out. So this is not even a series that we know anything about. So let's pick something that we know something about, but it's still inside of here. So we're going to compare it to the sum from n equals 1 to infinity of just 1 over n. And this is a common thing that you'll do, is if you have a trig function especially, and with some argument in here, and you're trying to find out about the series, you probably want to compare it to the thing that's inside of the sign. So we're going to compare it to 1 over n. And how do we figure out this limit? Well, if we plug in infinity, this is 0 over 0 now, right? So what are our options for figuring out that limit? Yeah, one option is we can do a U substitution, or another option is we can just use L'Hopital's rule on it. So if we want to do a substitution, we can do U equals 1 over n. And if U were to equal 1 over n, that's going to give us sine of U over U, which is very convenient, very conveniently a limit that we know if our variable is approaching 0. Well, if n approaches infinity, what does U approach? U approaches 0. And so what do we get? We get 1, which tells us that since this is a finite value between 0 and infinity, either our series and 1 over n both converge, or our series and 1 over n both diverge. And what do we know about 1 over n? It diverges by the p-series test. And so by the limit comparison test, the sum from n equals 1 to infinity of the sine of 1 over n will also diverge. Does that make sense, everybody? Any questions on that one?